I'm going to invite Luca to the stage to talk more about Lightning framework, how it works, and how you can build your apps with it.
Thank you, Thomas. All right. Yeah, I need this one. Thanks, everyone. So I hope this was exciting. Now it's time to open the lid, have a peek under the hood on what's happening. Have you seen Lightning AI can go anywhere from building demos to orchestrating full ML systems, to building them, and without requiring a lot of cognitive overhead. And I think cognitive overhead today is kind of a curse in ML, because you need to compose things at the finest level of granularity. It's like building a car, actually getting a bag of screws and tiny things, and you need to put the car together, which you can do. But maybe sometimes you don't know what you don't know. So this opens up the possibility for you to get to the end result without having to know everything, and maybe then you can dig in and know more. But it's a bit like kids learn, right? They learn to babble words, and then they can associate meaning to it, and they can discover their way through it. So this is the way I kind of think about Lightning AI and what it enables today. So when we started thinking about how to empower Lightning users to do more than training, to go beyond training, to tackle distributed computing or building full ML systems, we wanted to overcome a few challenges. Computing at scale. The trainer gives you the ability to abstract away the way you distribute computation across machines, but it doesn't solve you the problem of how you provision those machines and how do you make these things come up and ultimately communicate. Or if you don't use PyTorch Lightning Trainer and you have to do other things like inference and so on, how do you make them communicate? You need to learn REST APIs or other protocols, gRPCs, and so on. It's a lot to learn. And then, of course, when you wire everything up, then you have the problem, what if this machine goes down? Everything breaks, and it's not great. How do you build a system that is inherently fault tolerant? It's a great problem. It's a big problem to solve. And typically, if you have ever done this, having a possibility of simulating your system in your machine in order to understand where the bug is and how you fix it or how it will behave once it's at scale without actually having to SSH and look at logs on a Kubernetes UI like Lens. It's really hard to build a system locally that has the same properties of the system on the cloud. And so this is also a problem we wanted to solve. And do it in just code, just your Python code, just like Lightning. And there's a lot that happens in PyTorch Lightning that it's a bit like this. There's a lot happening that could be happening using configuration tools and so on, and it feels just like code. You can understand it, you can relate to it. How can we bring this concept to building cloud systems, full ML systems? This is the challenge we set out to solve, and I think we have a possibility to solve this today. So we introduced 3 new abstractions, like William introduced at the beginning of the keynote. We have app, flow, and work. These 3 guys will allow you to build the systems you want. Let's take a look at a sample application. A robot. So robot needs to explore, and you want to save its parameters where the exploration is great. So what you would do to build such an application is you would say, okay, dear robot, just keep exploring and collecting your score. So this thing is actually a blocking thing. It's a while true. It will never exit. But then you would want to say, okay, now I check if the system is ready, then I start my robot, and when the score of the robot is more than 1,000, which is a nice number, then I'm going to save the good parameters, because this robot will have unlock the right way to explore its environment. If you have this app, all you need to do with this app.py file, you just install your Lightning framework. And then if you want to run locally, you just go lightning run app.py, and it will run on your system. Or run lightning run app.py -- cloud, and it will be deployed on the cloud. Okay, so we talked about Lightning app, Lightning flow, and Lightning work. This is Lightning app. It just runs things. We'll dive a bit more into this. This is Lightning flow. It just coordinates things. This is the way the robot should, I should guide the robot to do what it needs to do, provided that the robot is a self-propelling thing that it will just do its exploration. So how do I orchestrate what the robot is doing and then make decisions? This is what I'm doing in flow. And then the work is where the grunt work is happening. Let's dive a bit more. So the first abstraction, Lightning app, I pass it a flow, and when I call lightning run app.py, this will be executed. So this is just like a runner. In fact, it might be reminiscent of the trainer. Trainer is not a class, you subclass. You take a Python module, you pass it to the trainer. Trainer is just like a runner. It takes care of running things for you. And in fact, you have a trainer, you have a model or Lightning module within it. Same way, you have an app, and you pass it a flow, a root flow. And we'll understand in a minute why I use this word root flow. All right. Flow. As I said before, and as William has introduced a while ago, it has an init with some attributes, and then a run method, which is what dictates the logic of my flow, how it orchestrates. This is called the state. Flow is a kind of a peculiar construct because you cannot do everything you want with its attributes. They have to abide some rules, but essentially whatever gets set here prescribes how flow should happen. It's a bit like a function. You give it a state, which is the set of attributes, and then the run method will only see this state. So its behavior, what happens here, is a function of its state and not anything else. So the state can be checkpointed. So if I take a flow, I take a state from somewhere, stick it into the flow, run the run method, it will run. If somebody else took the flow somewhere else and it saved its state somewhere else, then you can stick that state in the flow and it will have one flow of execution that it will be solely dependent on its state. In other words, its only side effects happen through the state. How does that run function run? How does app call the flow.run? It calls it repeatedly. So we said you take the state, you pass it into the flow, and then the flow will have one pass of the run function. Well, this happens repeatedly, every fractions of seconds. It's a bit like reactive programming, Streamlit, if you have done Streamlit, or React, if you have done front-end programming. It's just like that. Given a state, it will make a pass. It's like immediate mode rendering for the OpenGL guys in the crowd. It's the same thing. It's immediate mode distributed systems. So you give it a state. Given a state, it will have a flow of execution here. It will generate state changes, and then the state changes will be merged into the state, and this thing will continue to happen over and over again. We have a 1-second rule. You will get a warning if your run function takes more than a fraction of a second, because the run function is not meant to do any actual work, but it will just coordinate logic. And what you can do, though, is you can stick as attributes of flow other flows. So you can build a tree of components that will have their own logic. So this run method here can call or may not call, depending on your logic, the run method of a child flow, and so on and so forth. So you can actually compose logic in a tree. Basically, you can have, I don't know, logic for an active learning thing that will need to train something with logic from an HPO run down here, so you can stick them together. And same thing, given a state for the whole tree, the behavior of this composition will depend on the state and will generate state changes that will be then merged into the main state. And the flow is unidirectional, just like React, just like Streamlit, just like all the things I've said. All right, so this is flow, but where does the actual meat of the thing happen, right? Where does the computation happen? Well, in this guy, Lightning Work. In this case, if you can see, we said 1 second rule. Well, this is not a 1 second thing because it has a while true. It will block forever, right? But this is good. Work is there exactly for this reason, to make long-running computations happen. And so you can stick work as a child of flow. And the rule right now is that work needs to be at the leaves of this tree. Okay, so you have a tree of logic, and then you have work with blocking thing, heavy computation, provisioning new machines, and so on. We'll see it a bit later, at the leaves of this tree. But the rule never changes. Work has its own state. State will dictate how this whole tree of things behave. It will generate state changes. State changes will be propagated back into the main state. The interesting thing is while our robot was exploring, it was generating scores. And it was sticking scores for the exploration inside the state. Those state changes were immediately visible to the main state. So Flow could reason about what was going on in work. So it's not like a DAG system, which is great for certain things, where each block needs to begin, end the computation, and then when the computation is done, then you do something else. Everything can react immediately to what is going on in this long-running computations. So for example, epoch ended, good. I can take a decision. Or the new model that is going on has a certain performance, great. I can now dispatch my logic differently. All right, so work is for heavy lifting. Side effects. Side effects are good in work, not good in flow. Side effects for flow should only go back into the state. All right. This thing runs in a process or in a multi-processing thing on your laptop. But then, what happens when you move to the cloud? When you push this to the cloud, thanks to the properties that we built this system with, we can run this composition in one machine and then these others in different machines or different pods or different containers and so on. And if we want to run work in different machines altogether or even multi-cloud, then we can split the whole thing, break it down, and run it at scale. So this can happen for hundreds of work, right? So now we have a tree of flow that is coordinating a fleet of work that can reactively send their state back. And this is how Lightning AI works under the hood, essentially. All right, so summarizing. We set out to resolve this problem. We think we're onto something here, and we're kind of going all in on these abstractions and building a whole product for the community to build things with. And we really hope this will empower the community to build stuff that will be characterized by distributed computations at scale, that are reactive ML systems that are dynamically reacting to change into what happens within work or within the logic in a really easy way, in a way that I don't have to think about how two machines communicate. All I need to care about is how my state evolves, which also gives us an opportunity to build a fault-tolerant system because now we can say, okay, this work failed, what should I do? This is a state change again. And I can reason about my system on my laptop because it will have the same characteristics of what happens when I distribute it on the cloud. But the most powerful thing, I think, is going back to what we said at the beginning, building the car. Right now, with this, you can build components that are apps themselves. But since the app takes a flow, and the flow can have multiple flows and work behind it, below it, somebody else will be able to create something with a flow that will, into which they can stick your thing, and now we can build on each other things and build more and more complex ML systems together. Because if I create an HBO component and you create an active learning component, now you will be able to use my HBO component into your active learning component, for example. There are a few other things, like Will has anticipated before, a shared drive that works locally and on the cloud. We have payloads, which is ways of passing very large binary things through the state. For example, a batch of tensors. I want machines to work, for example, to publish their, parameters, and then I want flow to dispatch those parameters to another work, and this is the way I do it. And also, we can enable cross-work networking. So, for example, you can build a huge DDP cluster that is managed through the flow state changes by having work communicate together as a cluster of machines. All right. Build ML system in days. Focus on what matters. It's really similar to the PyTorch Lightning ethos, but it's taken to the system level. Thanks.